everybody to this new offering from the UNESCO Chair in Disaster Risk Reduction and Resilience Engineering at UCL. Today is the first of our 2 days courses for 2023. And it will focus on system resilience applications of Bayesian network for decision-making in civil engineering problems. As I mentioned, this is not, however, the first of the offering from this year. We had in February a webinar from Martin Schildkamp on non-engineered seismic design for masonry structures, which was very well attended. And we do have a packed program for the next few months. And indeed, in a couple of weeks' time, we'll be holding a second 2 days course on the application of Selena. Selena is a seismic risk assessment platform to urban and regional scale. And this will be delivered by Professor Sergio Molina from University of Alicante and Dr. Abdelghani Meslem from NORSA agency that works on disaster risk reductions from Norway. We then in April have two offering on structural resilience this time rather than system resilience, focusing on strengthening and retrofitting of concrete and masonry structures. And this will be offered by Dr. Reida Tikhari and Dr. Rafael Fernandez from our chair. And then in May, we will have a second offering on system resilience, and we will look at the use of agent-based modeling in decision-making and disaster risk reductions and the use of neural networks. You can find more information on all of these on our website, and where you will also find news. And in particular, if you go onto the educational activities page, you will also find all the recording for each of our webinars and courses, which you can access on the Epicenter YouTube channel. For today, we have a very packed event, and tomorrow indeed. So we start with an introduction to probabilistic modeling and Bayesian network offered by Dr. Pierre Gell. The ones of you that have already visited our website will have seen Pierre CVs on the ground. Pierre did a PhD with us here at UCL and is now one of the senior researchers at DRR&RE, the geophysics office and services for France. We will then have some example of application presented by Dr. Asana Paramal-Vatteri, also a PhD from UCL and from this group. She will exemplify some of the application that we have carried out so far and that others have carried out so far. Dr. Ji-Yoon Byun, who had a PhD from University of Seoul and is now a lecturer at University of Glasgow. She spends a little bit of time at UCL as a research associate as well as Pierre, and she will illustrate first some Bayesian network analysis, the basics of Bayesian network analysis, and then she will do an introduction on a hands-on example that we hope you will get your hands on indeed, so that you can get more familiar with the methods and procedures that we will use, that are used in order to apply Bayesian networks. The discussion on the example will continue tomorrow afternoon at the same time. And then we will look at a series of case studies from Pierre, Asana, and Ji-Yoon at different scales and with different approaches. And finally, we will have a panel debate And we have invited Professor Daniel Straub, Dr. Enrico Tubaldi, Dr. Emin Menteses, and Dr. Dexter Lowe to present more and to discuss the issues that are raised through the course. We will present them more in details tomorrow. Before we start this work today, we cannot but have a moment of silence in reference to the Turkey-Syria earthquake that occurred on 6th February 2023. I don't want to give you all the statistics of the event, which are filled in our television sets and our news, but I just would like a moment of silence and a minute of silence while we are reflecting on the extent of the damage that we have seen throughout. Thank you all for observing that. And of course, we need to reflect on the causes of this damage, and we need to reflect on the responsibilities for what has happened. And of course, as engineers, we are called into questions every time disasters occurs. What we are going to discuss today is going to be of any help to this. Well, through some of the work that we have done and that you will see in the next hours and through the course, we can really start, and the Bayesian network has the power to really make us understand the relationship between the structural capacity, the magnitude of an event, but also its location and its different ways of affecting different elements. We can define casualties and among these elements, and therefore we can drive better our understanding of a problem, but also understanding where are the uncertainty and how we can express these uncertainties in probabilistic terms, and therefore how we can drive conclusions. And this can be done in order to improve our technical understanding of a piece of infrastructure, or indeed so as to understand better the important relations of different level of decision scenarios and decision criteria on the way in which natural hazards affect our environment and how we can prepare in order to reduce those detrimental effects. And with this, I would like to leave you to the first presentation from Pierre. So Pierre, the mic is for you. Welcome everybody and enjoy the next 2 hours. Bye-bye.
Okay. Hello everyone. So thank you very much, Dina, for the introduction and for the opportunity to give this talk. So I will just sharing my presentation, and we'll start by discussing about. Everyone can see it? Yeah, it's fine. So we will start the afternoon by discussing the probabilistic modeling and how, let's say, Bayesian networks can fit in and let's say help us in this task. So first, we can, let's say, discuss about the role of uncertainties in a risk analysis. So a commonly accepted risk decomposition is that risk is the let's say, composition of a hazard element, vulnerability element, and then an exposure element. And one may also, let's say, have, let's say, a more X-wing view and saying that risk is only about uncertainties, actually. And because actually, if you had, let's say, imagine that if you had a perfectly known situation, this would lead to a unique foreseeable outcome. And then there will be no place for chance and for actually no risk at all, because you know if the situation is going to be, let's say, either a success or a failure, there will be no probabilities or uncertainties related to it. An example, let's say, is if you have, let's say, a given component of a capacity that can, let's say, represent the resistance of a component or a system. And it can be subjected to, let's say, a certain pressure or demand, like a hazard loading. And both of these variables, actually, if they are uncertain, they have, let's say, a various range of possible values they can take. And right in the middle, when they, let's say, when the demand exceeds the capacity, then you have your failure of your component. And this is, let's say, what we are interested in here, to actually quantify this and to check this modeling. Of course, it's, let's say, way more complicated than just two curves like this intersecting. And in most situations, we have a complex problem. For instance, you can have, let's say, many different types of hazards that can let's say, apply pressure on your components. These hazards may interact between them. Also, then you have a various range of components that can be organized into systems or subsystems, and each of them can be susceptible to different types of hazards again. And finally, how these components can subsystems and systems can be, let's say, be organized into a more global system of systems with, let's say, maybe various types of performance measures and so on of your whole system. So let's say you have various steps to focus on, like hazard assessment, vulnerability of components, and then also systemic loss functionality assessment. Let's say in all of these stages or steps, you have various sources of uncertainties that can come in at various stages, and then can, let's say, have to, let's say, propagate right until the end. And commonly, people, let's say, assume that you have, let's say, two types of uncertainty. So the so-called aleatory uncertainty is all about inherent variability or randomness of some physical quantities. For instance, variability of a ground motion for a seismic analysis. These types of uncertainties, they are supposed to be irreducible. So they are, let's say, inherent to the natural phenomenon. And then on the other side, you have epistemic uncertainties. And these represent let's say, the lack of complete knowledge. For instance, if you have an incomplete data or modeling assumptions, and for instance, if you have a model that you have, let's say, to define a lot of parameters, yeah, like the Young modulus of concrete, or like yield strength of a given structure and so on. These are, let's say, parameters. Maybe you have some unknowns, or let's say you only know the range of variation. And also you may also hesitate between, let's say, various models. And then also you have, let's say, competing models as well, that you can maybe, let's say, you have to choose between several models, and you cannot really decide at first. And usually we think that these uncertainties can be reduced, provided that you, let's say, you can come up with additional measures or testing, for instance. And a way to represent these uncertainties is through a probabilistic model. And this, let's say, is a combination of a random variable. So this covers, let's say, the potential realizations of an uncertain event. And also you have to associate it with a probability distribution, which quantifies the probability of occurrence of these various potential realizations. For instance, some examples of probability models is, for instance, the variable earthquake magnitude in a given earthquake-prone area. That can be, let's say, modeled through Gutenberg-Richter distribution, or let's say the distribution of peak drag acceleration at a given site can be associated with a log normal distribution, for instance. Or we have maybe some discrete variables, like the damage state of a bridge or of a building, that is maybe modeled with log normal fragility functions. So these are, let's say, mathematical models, probabilistic models that represent these uncertainties in these variables. And then, let's say, once, let's say, you have quantified these uncertainties, you can proceed to what is called uncertainty treatment. For instance, you have your whole list of, let's say, input uncertain variables, which can be grouped into aleatory epistemic uncertainties. So, like I said, parameter related or model related. They can be, for instance, sometimes they have continuous variables, sometimes discrete variables represented by some histograms here. And then for this whole range of possible values, you can perform risk analysis. And your outcome, let's say, is the loss metric Y. You can check the distribution of this loss metric. And then sometimes it's about, let's say, having a feedback loop through sensitivity analysis and checking which variables are, let's say, the most influent on the final loss metric, and which maybe can be removed from the risk analysis and so on. And there are various, let's say, approaches for uncertainty propagation. For instance, Monte Carlo sampling, actually just a sampling of random realizations of the various input variables in order to get a stable estimate of the probabilistic distribution of the outcome variable. And you have many, let's say, variants to optimize the computations and the number of realizations that are necessary. For instance, Latin hypercube sampling, importance sampling, adaptive sampling, and so on. Other techniques also are logic trees. They are an efficient way to represent and model epistemic uncertainties, especially when you have, let's say, a model-related uncertainties, because then each branch of the logic tree can represent, for instance, a different choice of modeling assumption and so on. You have also fault trees, event trees. They are commonly used to study propagation of disasters, accidents, or cascading events in industrial systems. And also Bayesian networks, which will be more the subject here of this discussion, is they, let's say, allow us to group random variables and their respective dependencies into a graphical model with conditional probability models. Here is an example, for instance, of the use of these various uncertainty propagation techniques. Is what is commonly used in nuclear safety applications, probabilistic safety assessment for nuclear power plants. Let's say the combination of, let's say, hazard curves. For instance, a seismic hazard curves with a probability of accidents for a given level of hazard loading. Then you have fragility functions of a wide range of nuclear power plant components, for instance. And these are grouped then into fault trees and event trees in order to, let's say, come up with the probability of dysfunctional situation, and then the probability that this incident or accident propagates to, let's say, various situations with, let's say, very negative consequences in an event tree. And from this, you can then compute occurrence frequencies and so on. And then now switching to Bayesian networks, there are, let's say, an alternative way. Instead of, let's say, using this whole architecture of, let's say, a combination of probabilistic models and then put into fault trees, event trees. Recently, alternatives have been sought to, let's say, organize this in Bayesian networks. And these, they rely on the Bayes rule. So let's say you have a probability of let's say, event A, given the occurrence of event B. That you can, let's say, invert the probabilities, in the sense that you can express this probability of A given B just as a function of a probability of A, which is, let's say, is called the prior probability of A, like a marginal probability. And then the outcome is the posterior probability, conditional probability, because you have, let's say, you have updated the probability of A given the occurrence of an event B. And then you have an intermediate this equation. You have you make use of the likelihood, which is the other way around, the probability of B given A. And usually you have a normalizing factor also, which is the probability of B, which is called, you can compute using the total probability theorem. And using this equation, you can see that this is, let's say, a very convenient way to update a given model once some observations have been made. For instance, let's call the variable theta, which is maybe a vector of, let's say, many parameters of a model. And then you have observed some data D that you can use as evidence. And then you are interested in, let's say, updating the distribution of theta given your data D. So P of theta given D, it becomes proportional to P, to probability of observing the data given theta. So this is, let's say, the likelihood multiplied by the probability of theta, which is, let's say, your prior assumption on the parameters of the model. And then Bayesian networks make use of this whole logic, but also by, let's say, structuring the data and the variables each with one another. And so actually a Bayesian network is just a directed acyclic graph. And it is, let's say, represented by a set of nodes and directed links. So directed links is just an arrow going from a start to an end node. And so each node represents a random variable, and each link represents a conditional probability relationship. So let's say a dependence between two variables. So here is, let's say, an example of 5 nodes that are connected to each other. So 5 variables, x1 to x5. So the nodes that have, let's say, no parents, so no arrows leading to them, are called the root nodes. And here we just, let's say, they are just given a marginal probability because they are not dependent on any, let's say, variables. But then you have child nodes, let's say, that are, let's say, defined by a conditional probability because they will depend on the state of their parents, x1 and x2. And let's say in the case of discrete variables, they can be represented by this conditional relationship, can be represented by a conditional probability table or CPT. So this is an example of such a table here. If you have, let's say, the probability of x3 given the state of x1 and x2. So you see that if you have a binary states in each of your variables, so let's say true or false, or value 1 or 2, you can have 2 to the power of 3, so 8 elements in your table. And then what is interesting, so that you can have with these Bayesian networks, you can perform probabilistic inference of unobserved values given your evidence. So let's say a first possibility is to perform forward inference, so like a predictive analysis. So let's say you just put an evidence on a root node, And you can just, let's say, go down the chain of events following all the arrows up to the end of the Bayesian network and update the probability of X5. Or you can perform a backward inference, so more like a diagnostic analysis. Let's say that you observe a given value of X5, and then you can update actually the variables that are, let's say, more on the top of the Bayesian network, and to maybe access the posterior distribution of X1 given X5. And this is, let's say, an interesting huge feature of Bayesian networks, this backward inference. And then when we apply this to civil engineering problems, let's say a very, let's say, generic framework is just, let's say, to have a hazard layer. So representing the green node would be, let's say, the probabilistic distribution of hazard values like peak drag acceleration and so on. Then the yellow nodes would be the state of maybe many components, so n components that are exposed to the hazard. And then these would converge to compute maybe the failure probability of your whole system, the red node here. So here, you have to come up with marginal distribution of the intensity measures of the hazard values. Here, the conditional probability tables would be fragility curves that are dependent on the intensity measure values. And then here, for instance, it depends if you can come up with a simple system, you have a in-series system or parallel systems that you can assess this from the state of the n components. You can access these. This comes with various problems because you have to check also whether you have some statistical dependence between the component events, like a common cause failure. And also here you see that they all, the n nodes, the n yellow nodes, they converge towards a single node, the system failure. This is a converging structure, components to system. And it's not optimal in terms of the size of your conditional probability tables. We have seen before that it was 2 to the power of 3 in the case of binary states, because we had 2 parents. And with n parents, you have a growth of your table size to the power of n. So this is, let's say, not scalable at all. Yeah. So in practice, let's say you can start by building the structure of your Bayesian network graph by let's say putting edges that represent dependencies between variables, maybe not necessarily respecting the cause to effect orders. Sometimes it's easier to maybe model or represent the probabilities the other way around. And of course, it is permitted then to have arrows the other way around, yeah. If it's maybe easier to model, for instance. Then you have to build these probability tables for each of your node, minding the size of these tables, like I said before. And then you can pick some, let's say, nodes that represent observed evidence, like maybe values that you have measured or that you have collected from the field. And then you can perform inference with a given Bayesian network software, and then come up with, let's say, the updated distribution, the posterior distribution at the desired nodes that represent maybe the variables that you are interested in. And we can maybe make a difference between, let's say, 2 classes of inference algorithms. You have exact inference, like junction tree, bucket elimination algorithms, and the sampling algorithms that are more like that are related to sampling let's say schemes. And exact inference is interesting in the way that it gives you exact posterior distribution, but also it's only applicable to Bayesian networks with discrete variables. With one exception is that a Bayesian network that contains only continuous variables with only Gaussian distributions. And here, how can we solve a Bayesian network? So we take again our example with 5 variables. And you can express actually the joint probability of all our 5 variables by doing the product of all conditional probabilities that are given exactly by each variable given the state of the respective parents. So here it's quite simple. In these 5 variables, you have a probability of x5 given x4 multiplied by probability of x4 given x1, and here you have x3 that is dependent on x1 and x2, and then you have your marginal your root nodes x1 and x2 that are just without parents here. So just and then let's say we want to know probability of x3 given that we observe x5. Then we use this Bayes rule, and then we can let's say compute the let's say the ratio of 2 probabilities. One is a joint probability of x3 and x5 divided by the probability that we had observed the given value of x5. And for this you have then to use this joint probability by sampling only on the possible values of all the other variables that have let's say not appearing here, so neither x3 and x5. So we can see that actually it's quite let's say mathematically it's quite simple. It's just a matter of products and summations on conditional probabilities, and actually just the let's say efficient computations are guaranteed by carefully choosing the order of the operations. So here is a famous example, is the burglar alarm Bayesian network. So let's say you have an alarm, and then you are away on vacation, and you ask 2 neighbors, John and Mary, to call you if you have if they hear the alarm. But actually they may not hear it, the alarm, and also there is a chance that they call you anyway, even if they have not heard it, and the alarm may be triggered by either, for instance, a burglary, but also maybe an earthquake that may trip maybe the alarm system. So you can build your conditional table, and then maybe you want to know that maybe Marie has called you to tell you that she has heard the burglar alarm, and then you may wonder what is the probability that there is actually a burglary given that she has called me. So probability of burglary, probability of B, given that Marie has called you, given M. And for this, like we did before, we have first to compute the joint probabilities. So you have to build a table with all the probabilities, with all the possible values of A and M, B and E. So this is just by multiply all the conditional probabilities. And then you have to marginalize and just let's say sum over all the variables that are not used in the problem, that are, let's say, that can take possible values. So you reduce your table, and we are interested in this case that Marie has called you, so the event M. We take this column, and also we normalize, and then the final result is this value, so around the 5% actually that there is a burglary. So you can see that it's not very intuitive, but actually the probability is actually quite low, even if someone has called you. And this was, let's say, an example with very few variables involved, only 5, and quite simple relationships. And you can just solve it by computing all the joint probabilities in a one shot, let's say, with all the products. But there are more efficient algorithms, are the junction tree. It allows you to, let's say, divide your Bayesian networks in subsets of nodes that are called cliques. And you can only then you can only have to compute the let's say the joint probabilities of each clique, which can have a reduced number of nodes. So it's very efficient inference. So we take our example here. So a step is to, let's say, to moralize the graph by, let's say, if you have 2 parents of a given nodes, you can join them. You have to join them so they form now a triangle. And then let's say you have to set up an elimination order. let's say you eliminate 4, and then you have to form a clique of variable x4 and all the adjacent variables, so x1 and x5. So this is one clique. Then you go on, you eliminate x1, for instance, so which you have removed x4 now. So which are the adjacent neighbors of x1? So it's actually all the variables that remain. And if you remove x1, you have x2 and x3, and then you come up with you have eliminated everything. So with this order, we have formed the 2 cliques. But actually, if we have picked another order, you can have a reduced. Maybe you have more cliques, but they have less variables, less nodes inside them. So this is the optimal normal order, because it comes up with a smaller size of conditional probability tables. And this is something, let's say, that also is difficult to assess in advance, or let's say to find the optimal order of elimination, for instance. So it can be a complicated problem, and to find the optimal, let's say, solving algorithms for your Bayesian network. So just to conclude, we have seen that there is a need for tools and models for the propagation of uncertainties, from the source event to the estimation of losses. And Bayesian networks may present many benefits, like the integration of predictive models with observed data. So this is the case of backward inference. It allows for accurate modelings of complex systems, because you may take care of various correlations and so on. And also in the case of exact inference, you can generate exact posterior distributions, which are useful for the exploration of extreme events, of, let's say, very seldom combinations of variables, for instance. And there are multiple applications, so you can use them as a decision support system in the case of rapid response to, let's say, a disaster. You can use them to extract exact joint failure probabilities, or you can use them for uncertainty propagation in the context of imperfect knowledge. But there are also some open questions, like the scalability of Bayesian framework when applied to larger systems, and also whether to use only discrete variables. If you have a continuous variables, should you discretize them or use continuous distributions, and so on. So I finish here. Yeah. Thank you very much for your attention. And these are just some projects also that have helped us develop this work. Yeah. Thank you.
Thank you, Pierre. Yeah, I would suggest that if people have questions on the particular session, should we take this now, or we can leave it for the end of the session? Or you can also type your questions into the chat if that's preferable.
You can just open your mic if you have any questions and ask.
Hello.
Yes, hi.
Yeah.
Can you please introduce yourself?
Yes, hi. My name is Sohail. I'm working in Hatch, which is an engineering consulting company, and I'm working in the risk analytics department. So one of the things that we work on is Bayesian networks. And I actually wanted to ask Pierre about the concept of cliques. And can you explain a little bit more about that and how it helps or adds value?
Yeah. So actually, maybe I realized that I did not have enough time, so I rushed too quickly this part. Maybe it was too. Yeah. So a clique is a way to break down actually your Bayesian, when you try to compute a joint probabilities, you either, instead of, let's say, computing joint probabilities of all variables that are inside your Bayesian network, it helps you to only compute the joint probabilities of, let's say, a subset of variables. And this subset is determined by the the dependencies, whether each given node has many parents, or if it has if it is, let's say, how well it is connected to other variables inside the Bayesian network. And it depends also on the way, let's say, the order that you assemble the cliques. Yeah, like you have seen that you have various possibilities, and it is not it does not give the same amount of cliques and the same size each time, depending on the elimination order.
So it's mostly to simplify the conditional probability table?
No, it's when you, let's say, yeah, if you more like after, when you try to solve. Because let's say conditional probability tables, they represent the rules of your Bayesian network. They can be very big. But then when you perform the inference to compute joint probabilities, you even have to multiply and to probability tables with each other, which then, if at this stage, even further, let's say, make this size, the size of the tables
bigger,
even more. So it's really a problem related to memory and to stuff like this. And but I'm sure, I think Ji-Hoon will talk maybe later or tomorrow about these issues also. And
got it. Thank you.
Yeah,
You're welcome.
so spoiler alert. Yeah, we are going to talk about these problems tomorrow, and I personally developing a Python package to address particularly this type of problem. So if you're interested, yeah, just let me know.
So we have a question in the chat. By connection between variable in the Bayesian network, do we mean correlations?
Not necessarily, no, it's more like a statistical dependence, or even like a, it's more like
yeah, I think it's a kind of a like it's just terminology, but yes, when they are directly connected in a graph, then that means they are like there is a kind of a directional and direct dependence between these two nodes. But but between nodes that are not directly connected, but there are some arrows that we can just track down, then that means they are statistically dependent. But correlation is used to usually it is used to express that they are statistically dependent, but they do not have this directions. So they are kind of bidirectional. So like, and the Bayesian network is depends on this directionality of dependence. So correlation is not much used term in terms of Bayesian network, but they all mean statistical dependence.
Are there any other questions? Thank you for the question, which help us also to establish more definition and ground rules at this stage so that everybody can follow better. There is a hand by Ashta Puder. Would you like to ask a quick question? Can you introduce yourself, please?
Hello.
Yes.
Can you hear me?
Yes.
I have a question. Like, for example, now I am working on the interdependencies between different critical infrastructures, and how efficient would be Bayesian this method for a very dense network? How efficient would it be? Like,
who would like to answer here? It's quite difficult to decide how efficient it is without knowing exactly what the architecture of the network is and the infrastructure.
Yes, but I think the main advantage of Bayesian network is this visual representation of dependence between random variables. So so it is useful when like we can identify the causal effects between variables. So when there are multiple types of variables, for example, there's hazard components and then deterioration components, and we have some observation nodes, and we have a component system. Then, but we kind of know that how they affect each other in a kind of directional way, that deterioration affects the performance of the components. In this way, that we can visualize the complex dependence between random variables, and then it helps us formulate and inference the probabilistic models. But it is not very helpful when there is, for example, if it is some kind of a Markov random field, that everything is correlated, but there is no direct or like causal dependence between these random variables, then it is not something that you want to apply Bayesian network.
Thank you.
You're welcome. I think we can possibly move on.
Thank you for the questions. Yeah, I will start sharing my screen. We can take more
while you are doing that, there is
session.
another question.
Okay.
So
Okay.
for risk, while you're preparing your screen, I will read it for Sanjeev Kapoor. For risk assessment of civil structures in seismic zone, what is the reliability confidence of BN as compared to other models?
I don't know, I would say that they are only as good Bayesian network as the, let's say, the type of data that you feed into them. You know, if you have a very good knowledge, nice earthquake catalog, nice ground motion models, and of course, if you put everything in Bayesian network, there is no, they will compare, very well to our methods. They are not, let's say, for me, let's say it's more a way to organize your variables and to use as a, let's say, decision-making tools as well. Yeah, to have, let's say, then.
It might be better than other random approaches, because here you can define the causality between a set of data. So, and that helps you to actually constrain the way that parameters influence each other. While if you are doing Monte Carlo simulation with a random model, you don't really know what is the relationship between the parameters. There is one.
I agree. Yeah. So that like inference wise, it doesn't have any reason to be more accurate than other probabilistic methods, but it helps us modeling when things are complicated.
And I think, I mean, the capacity to do an updation every time you have additional information in terms of the evidence is the added component here. Yeah.
Certainly, Asana, very good point. There is one more question which we leave for a little while, because it will be very good to discuss after this second presentation, which is about the suitable inference algorithm for different applications. So let's look at a few applications and then we will discuss that. Thank you very much, Monica, for asking the questions, and Asana, please proceed.
Thank you, everyone, for joining the session. I hope we have a basic understanding of what a Bayesian network representation looks like and what kind of problems it is suitable for. So some examples from the perspective of structural and infrastructure system modeling, we can look in this section. When we say a system, it can be composed of, it can always be decomposed into several elements, several components, which then form a series or a parallel system, and together which they form the system. So the reliability of each of these components and them as a series or a parallel subsystem would then influence and decide what the reliability of the system is. So in any of our problems, first thing we want to do is the modeling of the structure of the Bayesian network, which is often done by a knowledge representation. As Pierre was mentioning, we kind of know the interdependencies between the cause or the effect of certain components, say, for example, the hazard causing damage in our structure. So what are different, how the different variables interact in the system. It can be input as a structure of Bayesian network from an expert knowledge in the domain, or from conducting expert interviews and so on. Other methods of doing the structure modeling itself is if you already have an existing method like fault tree that you have developed for the problem, then that can be mapped into Bayesian network. And the third option, which is very rarely used in structural engineering kind of problems, is learning the structure from data. So if you have abundant data source of deciding the structure of your network itself from the correlations and dependencies between variables, that is a problem, a machine learning problem, but rarely applied in civil engineering problems. And in the second, once you have the structure, it would be then to decide the parameter modeling. So for each of the variables or the nodes that we have identified in the structure, if they are root nodes, we need to have their marginal distributions or original root distributions. That is the states of those nodes and their corresponding probabilities. And if they are a dependent or a child node, we can then have to define the conditional probability tables based on how the dependencies with the parents. So for these cases as well, we can have these three approaches of modeling, say, for example, the expert elicitation, and then the mapping from other methods, and also the learning. And once we decide the parameters and the conditional probability tables, is when we can do your inference. So this is where the inference algorithms come in. So as Vera explained, we can have exact or approximate inference algorithms depending upon the size of the problem and what is the intent of your work. So once you have this, the last component is to do kind of validation, which is in these cases many times done through sensitivity analysis or using real or simulated data. Say, for example, you know certain relations between variables and how they increase or decrease, or definite states of certain variables affect the states and the occurrence of other variables. So with that as a very basic background, we will then look into our specific case of structural and infrastructure systems applied to several normal load cases like gravity loads or single hazard conditions or multi-hazard actions, and also a small component of structural health monitoring. So I think the very first starting point could be a very simple structural case where this study in 2001, probably one of the very initial attempts at extending Bayesian networks into core structural engineering problems. It was to look at the structural system as composed of several components. And then, say, for example, it's a two-bar system. If it's a series system, you know that either component failure means the system failure, or if it's a parallel, both of them have to fail to have a system failure. So this is a very simple, intuitive representation of that system into the Bayesian network. And however, if not purely correct, in the sense that, as we previously mentioned, there could be correlations between the component level limit states. Say, for example, the A and B in this original network seems to look independent. But however, there could be statistical correlation between the states of A and B. So this could be, say, for example, the load that is applied to the system, which influences both of them similarly, and also the individual strengths of these components. So if there are correlations among these input parameters, then the components A and B are correlated components, which can also be input as a different or a new node into the network. So this is one way of introducing these additional statistical correlations into our Bayesian network. So something that would be very useful in our kind of problems, civil engineering problems. The other constraint or the concern regarding this is multiple failure sequences. So it's not just the independent existence or failure of components A and B, but also what happens and how the total system failure is influenced by the sequence, like when one of the component fails, it then affects the failure of the other. So this, say for example, if you don't consider that kind of an interaction in a series system, you would define your conditional probability tables for the system failure in this particular manner, where we have either 1 is failure, 0 is survival, say for example. But if you have this kind of sequential correlations to be addressed, one way of doing it is through considering modifying the conditional probability tables such that when you are given that one component failed, then the failure of the other component will be dependent on, will be modified. There would be an updated probability of failure of the second component given the first component is failed. And this will be, it's the same as the system failure, because for a parallel system, the first component is already failed. So this is a simple explanation or example of how we can include these kind of additional considerations into Bayesian network to model civil engineering problems. So this particular example, we looked at 2-bar system. We can always have larger systems by expanding that, but bearing in mind that the CPT size increases with increasing number of components. So say, for example, you have a 3-bar system. So for each of the failure cases, we'll have to then consider various combinations of failures. And also it would involve several subsystems. Say, for example, in the 3-bar system, if your 1 bar is failed, then the other 2 would look similar to a 2-bar system. So that becomes a subsystem, and subsystem failure analysis will be needed. So it keeps on increasing with the number of elements, number of failure combinations that we are looking at. So in particular study of this particular study, they were looking at frame structures with number of hinge locations, that a combination of which can lead to a failure mechanism. So one way of reducing, you don't want to be looking at every possible combination and every possible node formation, hinge formation, because practically there are cases which are probabilistically more significant than the others. So the algorithms such as branch and bound concept, for example, that will allow you to have a bound of more probable dominant failure sequences, so that you can reduce the number of iterations, the number of steps in the problem. And for this particular study, it was, as we previously discussed, it's not very different from existing or other statistical tools for computing the probability of failure. However, this was much more advantageous in terms of backward propagation when you have a certain observed variable, then how the other variables get updated. So this was a very simple frame structure, which is under gravity loads, a case that was applied. Another a bit more towards the hazard risk assessment example is here in terms of seismic risk management. So here now we have components of exposure, vulnerability, and robustness. So in this study by Baraktali et al., this was modeled as a seismic demand on the structure itself is then dependent upon what is the earthquake magnitude, the distance, again, soil type, where the location, and also the fundamental period of the structure. So these variables could influence what is the seismic demand on the structure, and hence what is the damage experienced by the structure. And this damage experience, as we previously looked in, can be captured through fragility functions, which relates to the seismic demand. But again, that involves the level of model uncertainty, which can be input at this stage. So this also shows a capability of actions and action spaces, or it's called the influence diagrams, where you can have an intervention such as you are deciding to do certain strengthening treatment for the structure, or you're not going to do that. So this then influences what would be the damage and what would be the fundamental period of the structure. And then you can update what you can observe what is the consequence of each of the actions to make a better decision in a decision-making problem. So this is a straightforward computation of direct and indirect consequences For example, the direct consequences would be from the probability of the seismic event occurring, what would be the IM or the intensity measure given that event occurred, and then what is the EDPs, the engineering demand parameters, given a particular IM is available, and then what would be the damage corresponding to a given EDP. So in same way, the indirect cost is connected to the damage, and then what would be the cost associated with that damage. So this is setting the framework for much larger and wider problems. It's not just in the case of seismic risk management. So I think it can be expanded to other problems as well. So this particular example of applying that framework was given by the same researchers. And if you look at it, you can also look at specific approaches they have identified for each of the steps, like the exposure, vulnerability, and robustness. So the robustness was basically defined in terms of the consequence from damage, economic, and casualty. So the modeling of these also involve a lot of uncertainties. So identifying the damage level of the building and then converting that to the cost or the associated casualties. So this will be our next case of importance. And I think this is useful for several of the civil engineering problems. And now we looked at just one hazard case, which is the seismic case. This is an example of a multi-hazard assessment on structural systems. A bridge system is shown here. And this is one of the case studies we will be discussing in detail tomorrow by Pierre. So I won't be explaining so much, but in this problem, earthquakes, floods, and ground failures were considered. And a framework was developed to see how the component level fragility functions can be then homogenized to a functional level loss assessment. So for that particular derivation, Bayesian network was used in the case of a bridge structure in this study. If we move from structures to infrastructure systems, this is a case of a single hazard affecting an infrastructure of say spatially distributed assets. So in this case, one of the main concerns that is different from individual structural analysis is the seismic demand that is distributed as well. So in some cases like this one, Benzitor, this a very detailed seismic demand model was first created using Bayesian network, where you consider the fault coordinates, their geometry, and how the magnitude and rupture locations can be then modeled to identify what is the intensity, seismic intensity at a particular site within the infrastructure setting. So this is for an example that it again you can further detail what the rupture location. For example, you understand what is the rupture origin, but it can spread to either side of the fault, say right side, left side, and in relation to the distance of your site from the fault, the intensity at the site can be further varied. And in all of these, it's important to consider the uncertainty that is involved. Say, for example, the inter-event and intra-event modeling uncertainties, how well we are capturing it through the ground motion prediction equations and intensity calculations. So once we have, say, for example, the seismic demand taken care, then it would be the component performances that is the next component of the model. So for this, again, we can use numerical analysis tools, or say for seismic case, it is well-established linear and nonlinear analysis techniques are available to derive fragility functions. And that would give us what is the component performance given the seismic demand. So, and if you go from the component level to the infrastructure level, then you can further continue from the analysis of fragility, where you would be able to assess the state of damage given the IM, given the seismic demand, how your infrastructure system connectivity is affected. So in this particular case, the system performance was fed by say, for example, the first instant of the system model that we discussed, the seismic hazard model at each individual site is then influencing the component damage states. And this here, the structure, as we mentioned, it's again a converging structure, which is the system performance node as a child of all the component nodes. And that is where the computational bottlenecks come. So some of the approaches that are used in this study and several other studies to address this is to identify some sets known as the minimum cut sets, which because whose combined survival will ensure the system survival, or the minimum this is the minimum link sets or the minimum cut sets, where the combined failure of certain number of components will lead to system failure. So instead of looking at every other component failure leading to the system performance, it would then allow us to reduce the number of arrows that leads to one particular node. So that is one of the approaches. And also this is just in terms of one failure mode. There are also other, like we have a chain of events occurring, one failure leading to another failure. So it would be then possible to also capture the sequence or the direction of failure, and also how much how we can reduce or avoid several cases which are probabilistically very insignificant. There are also several other improved algorithms that are being developed to address these issues. There are also like simulation-based augmentation to this problem, where you can further reduce only what is significant using additional simulation. And the metrics-based Bayesian network, which June will be discussing tomorrow, is also a direct consequence of this, and we will be hearing from that tomorrow in more detail. Now we come to infrastructure system. In terms of the decision making. So we discussed addressing or assessing the state of the system. So for example, what if you want to have the influence of different decisions? So in this case, we can include decision nodes. Now, as you can see, the square nodes here, they are similar to other nodes, but their states will be different decision alternatives. Say, for example, this is a seismic demand on the system. You have a component here, the damage to the component. And the observation node here is maybe a sensor that you're able to read to understand the level of damage in the system. So if you have to make a decision of after a post-earthquake scenario, whether you want to inspect a particular component is a decision. So once you inspect whether the observation is made, and then you need to make a decision whether to shut down that component or repair the component right away, or some sort of decision. So in each of these cases, this will be associated with a consequence. Say, for example, the inspection will come with an inspection cost, or shutdown will come with a functionality reduction or time of inoperation. So this is also possible, and this has been applied to post-earthquake risk assessment in this problem, where several components in the infrastructure can be modeled, and the capacity of each of the component can be estimated. But again, here the problem is you have several components, and each of them can have several decisions based on their operation. So you need to have certain heuristics or decision strategies to go ahead with which would be the best alternative. So there are some techniques and optimization routes that are developed for this. Say, for example, value of information. That is, you need to have a gain in the utility from additional information. Say, for example, if you do make an observation, how much is that information going to help you with your next decision? So the final decision alternatives, the choice would be that gives the largest net benefit. So with this kind of a framework, they were then able to analyze a sample or a simplified rail system with components spread even on a point site components or distributed components. So, and the system performance was evaluated as the capacity of the passengers to move from point A to point B, and not just as a whole system, but maybe components of points from point A to B, B to C, C to D, and so on. So, and with this, we can then illustrate how we can update the decision-making process. Say, for example, you have different evidences provided. Say, after the first instant, you're given where the fault location is. So your seismic demand model gets updated. And then say, for example, you know what is the site intensity through some station in the site, or you know that the certain bridge component or a tunnel component is severely damaged. So say, for example, the fourth evidence, EC4, says that a component is severely damaged. So you know that your probability of reduced service is 100%. So in each case, with the availability of evidence, you can update what is the probability of reduction in service. So it was in the case of infrastructure system. It's a similar approach, but in a much larger system in terms of the transportation network was done in this particular study. And I think June will be discussing some of this in tomorrow's session as well. So this was a very large system model with more than 10,000 edges in the Bayesian network, and system resilience was quantified in terms of the access to the main roads from several smaller local roads. So in this case, there was a measure that was introduced, say, for example, reduction in functionality of a road segment as compared to its undisrupted state. So with that, it is able to, the system is able to identify what is the distribution of system level resilience loss. I hope we will be hearing more about this as well tomorrow. And this particular example and the next two examples will be our case studies from our research group. So we will be discussing this as well tomorrow. So this is the risk analysis of road networks, continuing from the bridge multi-hazard fragility function that I discussed previously. And this in the context of the road networks. And once you have the harmonized functionality loss model, say, for example, we discussed different component level fragilities and then hazard specific component fragilities going to harmonized functionality losses. So from that, you can then assess infrastructure system level loss by looking at the loss of connectivity due to the failure of the bridges. So this is the work done by Pierre, and we will be hearing more details of this. And the last case study from our group, this is my own work. We were looking at disruption analysis of school networks after earthquakes and flood events. So we did consider the physical combination or the effect of these two hazards on the structure in terms of how the material degradation occurs in the structure and then how the earthquake response gets modified. And in addition, we were looking at the functionality loss, say, for example, the inundation at school sites or in the locality of the school where people would then need sheltering in schools. So this particular aspect, which is not purely structural, is very decisive in terms of disruption in schools. So it is the capability of Bayesian network is also to account for less quantitative information. So this can be based on people's opinion and judgment, and we can then include statistics of those into the model. And the third component was the social vulnerability aspect. So there is evidence that socially more vulnerable people are experiencing severe consequences compared to others. So this is an attempt to model that correlation into the overall system disruption. And we then looked at certain non-structural mitigation measures as a way of reducing the disruption duration in schools. And this was by moving students from one school to another, which is less affected. So we will discuss the modeling aspects, which is definition of nodes and how the correlations and CPT tables are defined in tomorrow's session. We have now discussed both structure and infrastructure examples, and I think this gives an idea of how we can apply the Bayesian networks in kind of problems. And this is a different case where we have a structural health monitoring application where we are checking a dynamically evolving response of a structure when it is subjected to an earthquake. Say, for example, you have a sensor feeding you an information at a given time instant, and then you can get more and more information at different time instances. So the dynamic Bayesian network is used here in this particular work, where a Bayesian network is nothing but it captures the system states at each instant of time. So at each time step, it is acts like a different Bayesian network, but with a arrow going from the previous step to the next step. So that is why this is very useful for the structural health monitoring problems. Just to mention that we are more focused on the structure or infrastructure applications, but there are also other cases where Bayesian network can be applied purely for the hazard model itself. Say, for example, the sequence of hazards, or an earthquake triggering a landslide, and then triggering a lake, a barrier lake, where the landslide blocks a river. And then when the barrier lake breaks, it then goes and floods downstream areas. So this kind of a hazard model is worth mentioning, because many of us might be more interested on the hazard side or the vulnerability side. So say, for example, for each of this, we will have to provide inputs and then take out outputs from one stage of the Bayesian network and feed into the next stage. So what concerns is the input from the earthquake occurrence then affects the landslides, and from that the loose debris would go and then affect the formation of the barrier lakes, and then causing the floods. So it's just a mention that these kind of applications are also existing, and there are several studies which is purely on one single hazard. Say, for example, modeling the seismic hazard itself in great detail, also modeling only the flood cases, flood hazard in itself. So I think that I would not be able to cover all the possible cases and examples, but just to give an idea of the range of problems that is being applied, and which is very useful for maybe your own problems and further applications. Then these in the next session by June, we'll be looking at specific application and illustration. So before that, just to mention that we can use several tools to model Bayesian networks into of our problems into to account for the problem. So if there are MATLAB based codes that are available if you already have a MATLAB license. The Bayesian toolbox, which we have extensively used. And these are developed maybe by independent researchers or institutions, and some of them are available for free for education purposes. This PGMP-Y, we will be dealing our example using this platform, and I hope you have all received the email with instructions to download and install this package, and we will use this in the next session. And similarly, this particular toolkit is developed and it's made available by June herself. So you can ask more questions if you have with that. And there are some also commercial softwares which you can buy and use with more capabilities of maybe visualizing the network and having a better understanding and playing around the probabilities in a more user-friendly interface. So I think I will stop my presentation with that. If you have questions, please do feel free to ask. I think if we have reached the 1 hour mark, we can take a break, or we can move to the next session.
I think we went well over it.
Okay.
Maybe we can take some very quick questions at this stage and then have a 5 minutes break.
Yeah.
So there was a question about how do we choose the more suitable reference algorithm for our applications. I don't know if either Ji-Yoon or Asana you want to answer.
I think it depends very much on the problems, and if you're interested in exact inference, say for example extreme combination of events, rare events and variables, then exact inference will be a good option, which is not suitable for very large size problems. So I don't know, Jiyun.
Yes, I think if exact inference is possible, then it is always the most preferred choice. But if the problem is too large, then the exact inference would not be an option. Then that is when you need a sampling method or like other variational inference-based method. And especially between these Monte Carlo simulation sampling and these advanced sampling techniques, the reason that when you want to use advanced sampling techniques is when the probability that you want to measure is too low, that you will need so many MCS samples to get some confidence level. Then you might check using advanced sampling techniques.
Thank you. And Bahid Shafai, do you want to introduce yourself and ask your question?
Hello, everybody. Thank you for your excellent presentation. I just have a question about the example that you mentioned about the bridge, that you consider multi-hazard scenario, earthquake, flood, ground failure, if I think is correct. I just want to know, did you consider the integration between these hazards? Because I don't know, you consider ground failure that may be dependent on both earthquakes and flood, and maybe flood and earthquakes both separate and independent. And the other question on this part is on what scenario you apply these different multi-hazards for this bridge. Thank you.
I think, Pierre, that's for you.
Hello.
Yeah.
Yeah, so very good question. So very interested in this. So thank you. Yeah, I think I will discuss tomorrow actually as one of the case studies. We will discuss the Bayesian network for this bridge system in detail and how it can assemble the multi-hazard combinations and so on. So I don't know, will you be there tomorrow?
Yes, you
Yes.
should.
Yes,
Okay,
sure.
perfect. So I think you will know more tomorrow about this. But yeah, of course, we have considered some cases where both, let's say, we have two hazards that interact with each other to alter the vulnerability and the damage states of the components. So yeah, you have a exactly failure path like this. Yeah, more complex than just a single hazard. Yeah.
And
Okay,
Jude
thank you.
Hussein, thank you very much, Pierre, for the quick answer, asks whether the data can be pre-treated if the data set is too large. In other words, can you use dimensionality reduction techniques to render the data more usable? I think, Jiyun, that's something that you're particularly keen on.
Yeah, but in Bayesian network, the issue is not usually about the number of data. In terms of data, the more the better. But the number of variables matter. So so by dimensionality reduction, if you meant variables, then yes, they might be useful. But yeah, but data are not the factor for Bayesian networks complexity.
Thank you very much, Jiyun, again for the quick and sharp answer. I think very clear. Shall we have a 5-minute break and then we can listen to Jiyun's presentation. Thank you all. So we will reassemble in 5 minutes. Thank you. Hello again, everybody. I assume you are back there, and maybe we can resume, Gillian.
Yes.
Please.
Yes. So, since we are running a little behind the schedule, I'll just try to skip things in 30 minutes. So,
Yes.
yeah. So I'll just start. So this is the script that we shared earlier. We just received a couple of messages saying it was that some people had difficulties in running this script, and it seems that some of you might have forgotten to install this PGMPy package. So if you haven't forgotten, please install the package first on your machine, and then the code will run. So there are two, sorry, I was just, yeah. So there are larger two objectives today. The first one is we want to show that, like now, assuming that we are all on the same page, agreeing that the Bayesian network could be a useful tool to analyze a system event, then we'd like to show how exactly we can model a specific problem, particularly when there are multiple random variables and they have complex dependencies. And second, once we set up a graph, then set up a probabilistic model, then there is another story that we want to make some useful inferences so that we can use for actual decision making. And so this is our second objective today. So this is the problem. So we set up a very simple network, which can be interpreted as a transportation network with 3 bridges. And these bridges are subjected to seismic risks, which means that they can be disconnected when an earthquake occurs. And we are interested in the reliability of the system in terms of the connectivity between these two nodes. So these nodes can be interpreted as, for example, like a local hub and an airport, so that we want to make sure that you can deliver the stuff when an earthquake happens, or it could be a local neighborhood and a shelter zone. So, and you can imagine how this could be scaled up to a real transportation network for application. So this is the simplified example that we brought today. And regarding the second objective, we are gonna address 3 questions today. So first, what is a system failure probability? And this is to assess the current system's performance so that we can decide if the system is safe enough at the moment, or if one wants to invest more resources to retrofit the bridges so that we can ensure the system failure probability. And second, it's mentioned several times today, this Bayesian network can be updated using inspection data. So I'm going to show how we can update this system failure probability when we have more observation. And finally, we can identify the most important components so that we can prioritize the investment strategy across these bridges. So this is the problem setting. And so how I organized today's tutorial is that there are 3 parts. First, we have to set up the model, which is equivalent to setting up a Bayesian network graph. And then we have we need probability distributions for which we need data, and then we have to inform the program so that and this is the end of the modeling. And finally, we have to perform inference to address the decision tasks. So because we are running late, I will just briefly introduce the 3 parts in succession, and then I will just I will answer the questions after explaining all of this. So the first part is Bayesian network graph. So so this can be usually done by using causal dependence between real-world random variables. So here, this is how I set up a Bayesian network using for this system. So as you can see here, there is first this earthquake scenario. So the variable can have state mild, medium, or severe, and there are 3 bridges, and these D variables represent the deterioration of each bridge. So the deterioration can be either no or yes, and we can observe this deterioration status through these old variables, which will be also no and yes. And then we have this functionality of the bridges, which are affected both by the hazard intensity as well as whether or not the bridge is deteriorated. And finally, there is this system event, which is represented by this S variable. And the system functionality is determined by the functionality of these 3 components. So again, this system event has a state either survival or failure, and this goes the same as with the bridge variables, which also have the state either survivor or failure. So first, what we need to do is that from this PGMPy package, we need to import the Bayesian network class, which I called as BN. So, and in this package, what you first need to do is we call the BN entity. And so this is the variable name of our Bayesian network. And then we call this BN entity, and then we type in each edge that we have. So for example, we have this edges from earthquake nodes to B1, B2, and B3. So we have this EQ to B1, EQ to B2, EQ to B3, and so on. So it goes on with D1 as well. And you can see that there are all edges typed in. So I just run the code here. And now, since we have a graph, now we have to add all the distributions for each node. So there are 11 nodes, so we need 11 tables, and this is where you need your data. So in this example, I just simplify the state. So for example, for earthquake, there are 3 scenarios: mild scenario, medium, severe, and the earthquake being mild has probability of 90%, medium 9%, severe 1%. And for deterioration, there are 90% of probability of a bridge being deteriorated and 10% of not being deteriorated, being deteriorated. And the probabilities are all the same for the 3 bridges. And we also need this probability distributions for bridges. So for the first and third bridges, I use these probabilities, and for the second bridge, I set up this distribution. So as you can see here, For example, if the deterioration has not occurred and the earthquake is mild, then there is 1% of failure probability, and accordingly, there are 99% of survivability, but the failure probability increases and survival probability decreases accordingly as the earthquake scenario becomes even more severe. And if deterioration occurs, then the failure probability increases even for the same hazard scenarios. And I just set up the distribution for the second bridge to have higher failure probability than the first and the third one. And so for this, observe this deterioration status with some errors. So there are 1% of error that being false positive and 10% of 10 for being false negative. And finally, we need the system events distribution where which is usually deterministic because of how system event is defined using the component events. So since we set that system fails when the two nodes are disconnected. So if we go back to this network, then this network disconnects whenever this third bridge is disconnected. So if third bridge fails, then the system always fails. And if they are if the third bridge survives, then we can see that the survivor of only one of these bridges will connect the two nodes. So they are all connected except the case when both of the bridges are failed. Then in this case, the system fails as well. So so this is how we input this probability information in the package, using the package. So now we need this data structure called the tabular CPD, which I imported as CPT. And this is the entity that we defined before. And we say there is this module add CPDs, and then we add a CPT for each of the 11 variables. So for example, for earthquake node, it has 3 states, and each state has 90%, 9%, and 1% of probabilities with earthquake with states being mild, medium, and severe. And this goes the same with this deterioration nodes. And in case when a variable has parent nodes, then we have this B1 node, and it has this parent nodes, 2 parent nodes, D1 and DQ, and this one has 2 states, and these 2 parent nodes each has 2 and 3 states. And this is how we type in the probabilities. So this part, the table below, above shows the same order that how the package takes in the probabilities for this multidimensional distributions. So it follows this order, and you can see that the same probability values are typed in here. And then we also have to inform the state name for each variable. So B1, survivor or failure, D1, no and yes, which should be the same as the previously defined one. Otherwise, it will return an error message. And for earthquake as well. And for B2, we had different probabilities. And for B3, we had the same probabilities as the B1, but with a slightly different parent nodes. So, and for O1, it had D1, and I just typed in all the same probabilistic information. So it is quite straightforward, as you can see here. And it's the same goes with for S variable as well. So as you can see here, all we need to do is just type in the edges and then tell the Bayesian network how the distributions look like. So I will just run this block. And then a useful module in this package is that actually we can check if we typed the model correctly. Because sometimes when there are too many variables, then we might it is easy to get messed up. So if we run this code, then it says true. And if it is false, then it will give you an idea that some messages explaining where is wrong. So since it says it's true, I think now we are ready to make inference, which is the real fun part of Bayesian network. So to this end, we have to import this variable elimination module, which I imported as VE. And the variable elimination module is a variable elimination algorithm is an exact inference algorithm. So what we can do is that we can simply call the create this this entity that is an inference entity, and using this module, we create this one just by putting our model here. So if we run, then nothing happens, but now there we have this inference variable. And then now we can answer all the questions that we posed at the beginning of this session. So for example, what is the system failure probability? Then now we have this variable, and then we say we are interested, query means we are interested in a certain variable's distribution, and it is S because S represents the system event. So if we run this code and then if we print what S query looks like, then it looks like this. So it says that the system being survived is around 97%, and for it being failed is around 3%. So we have like 3% of system failure. And second, so what if we have inspection data? So then we can use this evidence option. So now we are still interested in the distribution of the system event, but we observed that the first breach was deteriorated. And if we run this code, then we can see that now all of the system failure probability increased, but actually we can see that this third breach being deteriorated has the most impact because mostly because of its importance in geologically, because if it is disconnected, then the system is disconnected right away. So as a result, its deterioration affects the system's performance the most. And finally, we can identify most important components. And there are many metrics that we can use for this, but today I brought this component importance measure, which is called the CIM, which is defined as a conditional probability that if the system fails, then what is the probability that the breach was failed. So in other words, this CIM measures the probability of a breach and fails given that the network failed. And this quantifies the contributions of each breach's failure to the system failure. So we can do the same as before as Q2. So so now we say that the evidence is now the system has failed, and what is the probability of this breach. And so we do that for each breach. And what we find is that for breach 1, the failure probability is around 20%. Breach 2, 28%. Breach 3, 87%. And what this means is that so now it quantifies and it compares different breaches. And we can see that the most important breaches are B3, and then B2, and then B1. And this is because B3 is the most important because of its location. And between B1 and B2, because B2 is more vulnerable, so it is contributing to the system failure more. So if we want to retrofit one of these two breaches, then it would be B2. And B1 is having the this effect on this on system failure event according to this measure. And of course, this measure could be different when we use different metrics. So this was the brief tutorial, and I'm happy to answer questions. And after questions, I'd like to briefly explain about the take-home exercise.
I'm sure that there are plenty of questions on this, just to make sure that everybody can follow and do the exercise for tomorrow, because that will be underpin our presentation and discussion tomorrow afternoon. So please engage with this. So there is a question from Anand. From where can I download the Jupyter notebook shared here? I did not receive it. Thank you. So this is one first fundamental step.
You mean the file?
I think yes.
Yes, ma'am.
Possibly he didn't receive the link. So maybe can you copy the link in the chat? Yeah.
Oh,
okay. Victor
you,
has
Victor.
already.
Thank you.
For us. Thank you, Victor. Any other specific questions on the exercise?
Then
it's everything very clear. It was explained extremely clearly by Jiyun, that's true.
Thanks.
But nobody has any doubt about applying the various steps, in spite of installing of Jupyter, Anaconda, PGMPI, and PyTorch. Now I can write the file, but now I can run the file, but figures are not visible.
Yeah, Asana, does the shared file include the figure?
Upon running the file.
So I believe in the G file, you would have this figure folder, and you also have to unzip the G file as it is. And then the figure subfolder should be in the same directory so that you can access the folder.
Yes, so Sanjeev confirmed that the figures are in a separate folder, and it's done once you unzip the file.
Yeah. So.
Any other questions? I think there were two questions, but were basically both about the figure folder.
Yeah. If there's no questions, then I will just
how you assign the conditional probability through expert judgment? So this is more generic.
Yes. So for this example, yes, it was just what the figures that I made up. But how we usually do is that for earthquake, we usually use a magnitude model, like GM ground motion equations, so that we can get the intensity measures, and then we use fragility curves to get failure probabilities of these bridges.
Given
for
the intensity at the site.
Yeah, right. Yeah, and also for deterioration models, we use deterioration models to quantify the conditional probabilities. Yeah, so each of these probabilities mean that we are using some models or data sets.
Okay, then we have a question from Monica Ariza. Does this Python package allows to plot the cyclic graph to verify we defined everything correctly? Likewise, for the CPT, can we check more in detail rather than check model true false?
I believe so. Because there is yeah, it's quite comprehensive and it is not only about Bayesian network. So you might want to check. But for example, it also has this function that you can list all the conditional independencies implied by this Bayesian network. So it has kind of a full functionality that you might want to take a look at. And for CPTs, I think there is by checking CPTs, I think you mean if the probabilities are summed up to 1, and there is a function that normalizes the given probability so that everything scales up to 1. So,
and there is one more question from Lombe Muntale, but maybe Lombe, you will have to articulate it a bit more because I'm not sure that I fully understand what you are asking. So what is the advantage or disadvantage of using learning to create your network or create CPT tables? I'm not quite sure that I fully understand what the question asks.
Yes, could you elaborate on this?
Lombi, are you there? Feel free to unmute yourself and talk about this if you want. Hello? You said you use expert knowledge to create the CPT table. Yeah.
No, usually, yeah. No, this was just an example, so I just made up the figures, but usually we use these models to come up with accurate probability. It's very hard to say a probability value is accurate, but there's some reasonable probabilities. We don't use expert knowledge that much in real problems.
Maybe I can complete. I think it's just can maybe use also empirical relationships, gathered from data. Use numerical models that you run simulations, and from this you extract probabilities and relationships. Yeah, so you have a lot of possibilities to populate the tables and
Any other questions? Okay, Lombe is now satisfied with the answer. Thank you, Lombe, for letting us know. If there are no other questions, amazingly, we managed to conclude. No, there is another one. Are you going to present an example of dynamic Bayesian network next session?
Not dynamic Bayesian network from my side.
Me neither.
I think that we will leave that to a future sessions where once people are more familiar with a static Bayesian network.
Yeah. And I also want to briefly, I will just have 3 minutes to talk about the take-home exercise, if it's okay, just so that.
Sorry, do you answer again?
Yeah, you have a take-home exercise.
Yes.
And if I could explain a little bit.
Yes, please, because people will be leaving soon. So.
Yeah, right. So I was just briefly, so I hope you could work on this exercise here. So I believe that you also had this script. And so this is the problem. So this is a figure that you saw earlier, which is the example developed by Gail and by Pierre and Dina. And so, and I just sneaked a little bit this small part of this bridge. And I asked the similar question that we addressed today. And I set up the Bayesian graph, BN graph based on the paper, but it is very much simplified. And I also typed in the, I just set up the district probabilities, but or again, these numbers are what I made up, and Pierre will show to all of us tomorrow that how we can we can actually quantify these numbers. So I just provided the information that you will need to set up the Bayesian network and then answer these questions. So there will, and at the beginning of tomorrow's session, there will be like a dedicated time that we will have your questions and discuss further. Yep.
Okay, that's great. As Asana said, you will find the recording of this session and tomorrow's sessions on the Epicenter YouTube. If there are no other questions, then please try your hands at the exercise and the take-home exercise, and we'll see you all tomorrow at 2 p.m. on the same channel. Thank you very much for attending, and looking forward to see you again tomorrow, also with the panel discussion. Bye-bye. Bye, everybody. And thank you again for our speakers today.
Thank you all.
Thank you.